This question about
Si tu vas dans l'affichage, tu fais toute ta page.
today.
Si tu veux toute ta page, tu vas dans
No,
l'affichage.
It's okay, we can all read the slide.
And about the Edwards experiment, I have a paper. You can take. I have also presentation of the YARK theory and physics with photons with non-zero rest mass, because it will be important for us. Now I hope it will work. Parce que je voulais bien entendu.
Excuse
There
me,
is,
can I, if we go,
you have larger one.
yeah, but if we, it's,
Le affichage. Affichage. No, affichage.
Affichage.
Yeah.
That one.
And you ask for full screen.
Yes, okay. Normal, the full screen.
It should be, the picture should be a full screen without the language.
Just go down, all straight down,
First slide, Jean.
down. There, almost no up,
Yeah.
up, to the right, 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 right there.
There.
Click it.
Good job, Anton.
Well, I'm in French, otherwise it would be.
Yes.
And
So,
the up-down keys.
a little story about mechanics, and you know all the Galilean relativity of mechanics in the 17th century. It has been extended to all physics, including the Michelson experiment by Henri Poincaré at the St. Louis Congress in 1904. And that was called principle of relativity. You cannot have something in the Michelson experiment because it's independent of the referential. So after that, you have the special theory of relativity, both by Albert Einstein in June 1905, and also sur la dynamique de l'électron by Poincaré in his note and in Palermo memoir. The Palermo memoir is something extremely rich with the Lorentz transformation, of course. It's Poincaré that has given that name, and the corresponding transformation of force, work, electromagnetic field, and so on, and even the first mention of gravitational waves. But that Palermo memoir for outside reason, political reason, nationalism, and so on, was ignored during about 30 years. And when it came to be known by the general public, the scientific vocabulary was so different that people consider it's difficult to understand, it's not clear. Poincaré has perhaps not really understood. So, it has been updated by two Russians in 1980 and translated into English and French. It's myself that has written the French version, this one, and I can assure you Poincaré was very clear and understand perfectly the subject. The two founding texts, that of Poincaré and that of Einstein, are of course they have a lot of common points, but there is a major difference. The difference is the second principle of Einstein. The velocity of light is always the limit velocity c. It's a principle. And because of that, photon must have a zero rest mass. If not, their energy would be infinite. For Poincaré and Lorentz, that equality is only an experimental fact with an accuracy that is not infinite. And it's essential to understand that the Lorentz transformation can be obtained directly without the constancy of the velocity of light. So, it remains the possibility that photons have a non-zero rest mass. Very small, but non-zero. And the velocity of photon will be almost equal to c with an increasing velocity with their energy, of course. In the YARK theory of gravitation, the photons have a non-zero rest mass, and we must understand what it means. The dual nature of photon, matter and wave is particularly apparent. They move in an electromagnetic field with a fast velocity field, and they have a group velocity smaller than c. And a lot of property can be deduced from this. For instance, aberration of star. The photon is coming from that angle A. It's a star there. And it arrives with the velocity g. So at the time -1, the coordinates are g cosine A and g sine A. Now, another astronomer is looking to this photon in a reflection v, with velocity v. Just do the Lorentz transformation, and you have the direction for the one. And the expression is very simple. You have tan A1 equal group velocity sine A over the gamma coefficient of Lorentz, G cosine A plus B. Oh. Now, consider the wave interpretation. You have there wave coming from that angle with velocity phi, phase velocity. And you consider the same Lorentz transformation in order to know what happens to the other astronomer. So, and you have the tan alpha, tan A1, sorry, equal something I don't write. Very simple, you have it in this paper. That requires this expression, in order to have the same direction, either for the matter or for the wave, and so on. So you deduce very easily a lot of property. The photon is a very mysterious quantic phenomenon, moving as a wave but appearing as a particle. It is a boson with speed 1, rest mass either 0 or extremely small. It carries energy, it has a frequency in a given referential, and present phenomena of polarization. That's all we know. Yeah, something very important. So, the energy of the photon in the referential of the first astronomer is this one. Very. Oh, I have. Yeah, this one. And you have also the energy for the second astronomer. You also may consider the frequency of the waves coming. The ratio of the two frequencies is equal to the ratio of the two energy. That means the photon have the same ratio h over nu for all astronomers, for all observers. It's the famous Planck constant, of course. That law is valid even if photons have a mass. If the photon has a small mass, it doesn't go at the limit velocity c, and we can study it in the referential in which it is at rest. Why not? And consider, I need another one. Consider a photon moving with a velocity g, somewhere there. He is inside a field with velocity phi, the phase velocity, faster. And here we have a wave-based lambda. So, for the observer here, the photon is a periodic phenomenon with a period phi minus g over lambda. But for the photon itself, that have a slower time in this referential, we must divide it by gamma. This expression can be computed by another observer with another velocity. It always gives the same result. The period of photon, sorry, I prefer to have it. It's very simple. If well, the proper period of photon is equal to the Planck constant divided by the rest mass of photon and the square of the velocity, the limit velocity, usually called velocity of light. So, all photons have the same period. In this it's a vibration or rotation, I don't know, something like that, but it fits particularly well with the property of polarization. Notice that if M0 was 0, the period would be infinite, and the photon would be not a periodic phenomenon. It's an argument, a big argument in the favor of the non-zero rest mass of photon. So, you have this relation there. The constant CH, usual constant, mass of photon, period of photon, frequency, and the variable in with that are a function of the velocity of the photon. So phi equal lambda nu, usual, G phi equals C2, we have already seen it, and so on. So there is only one parameter, for instance, the frequency with the proper frequencies there. It gives you G prime lambda. And it gives it to a small modification of Maxwell equations. These equations in back home are given there, the 6 usual equations. 2 of them are with electric field, magnetic induction, scalar potential, vector potential. And this one is modified into this, that one into that, with omega 0, the proper pulsation, 2 pi nu 0. So, we must apply it to the LIGO experiment, and I hope that I will be able to go directly to this. Yeah. Why it seems to be there? No.
There is. I think you need to get out of the first PowerPoint presentation.
I have it just before.
Yeah, it's this one. Yeah. You want to get this? This is the one we want.
No, but I have it.
Where's the other one? You need to go to the other one. Just go to the next one. Yeah, this one. Which one is yours? This one.
No,
That one, this one.
no, it's this one.
Yeah, but this is the one that we want to.
No, but I will have it.
Close this one and then go to that one. No.
Sorry.
You need to get back to this one. No, that's not.
Can we have a PowerPoint expert here, please?
I can't say that I'm an expert, but I seem to
No,
know a little bit more.
Yeah, I think he needs to close this one to get the other one working,
Okay.
because this one is blocking the screen.
I don't know what it is. Which one?
I have.
They change it somehow. I don't know.
Just really very.
They give the music. There's no copy more, is that right? Okay, 9 o'clock.
But it is not.
No, he needs to close this one.
Yeah.
He needs to close this window, because this one is blocking this,
Yeah. I'll just go to the other one, I think.
Where's my top tomorrow?
You asked Mr. Rich,
9 o'clock or something like
I've
that.
got no idea. I think it's close.
Yeah, but we close this one, not this one. You have to close it.
Is it correct?
Yeah, that's what it says. I'm not the one who programmed it. I was with
He said it's something that's changing. I don't know.
Fine. So,
Yeah, closing helps.
the kind of.
close the other one.
What's the name?
I don't know why, but that works. At least we can get hold of it.
Because it was.
No, just. Oh, that's cool.
Step up, right?
That would be That's the name, so
Yeah.
It says you can go low. I know it. I didn't know what they said.
Yeah.
Exactly. But you wouldn't let me do that.
No.
Now, you have seen the Michelson apparatus, exactly the same. In LIGO, you have 3 kilometers on one side and 3 kilometers north to this. Send a laser beam, come back, and so on, as usual in that kind of Michelson experiment. There we have velocity of light not exactly equal to the limit velocity c, and
Excuse me.
so
No, it's not.
it's not exactly equal to the limit velocity c, and we consider in this YARK theory that the collapse of two black holes is essentially an electromagnetic phenomenon with a huge quantity of electromagnetic energy released in a very small duration. So it gives, if I can have the next one, you will see the result of the theory right there. Yeah. So we have expected the red signal and the observation of the blue one, which is nice after all. So it gives an estimation of the mass of photon. We already know that the mass is smaller than 10 to the minus 50 kilogram through the analysis of the solar wind. And the estimation is about 10 to the minus 54. But it remains to be verified. And if I can go to the last, so ah, c'est terrible.
Non, vous allez... Non, pas là.
Voilà. Normalement, il devrait me rendre. Non. Ouais.
Oh, wait. There's no PowerPoint.
C'est pas grave, je vais la voir quand même. Voilà. Donc, thank you. I'm very sorry, I've forgotten to write it in Russian.
Can I ask a question?
Yes.
You had a very interesting slide on the board before you started LIGO.
Sorry.
You had a very interesting slide before you had LIGO. And it said div E equals minus omega 0 squared V. The equation.
Ah, yeah.
Okay. Now that equation suggests that the entire universe.
I will try to have it back. It's this one.
Next one. Next.
Yes.
The prochain. The next. Next to. Is Deutsches. Next. Yes, what is it? Le français. The prochain. I can't say it. The next slide. Yes, here. Top left. Div E equals minus omega 0 squared V.
This one?
Yes.
Yes.
This suggests that the whole universe is filled with
There is a mathematical difference.
a non-zero electric charge.
Yeah.
You also say that the whole universe would have filled in it the mass of photons. The mass of photons would supply the phenomenon of dark matter, and the electric charge would
Yes.
cause an automatic expansion of the universe and give you a phenomenon of dark energy. I find that two birds with one stone, we say in English. You could kill two birds. This was a lovely.
Yes, I see. We must remember that for any usual particles such as electron, proton, neutron, and so on, there are more than 100 million photons. So the photon is everywhere.
Yes, absolutely.
And if there are some slow photons, why not? It gives an explanation of tyrant light, which goes very well, because the photon with a very large velocity have a deviation almost nothing when he meet a slow photon. Yeah. I have the computation. It is very simple.
What is YARK theory of gravity?
No.
The explanation are by Mr. Tolker Yaman, and they are not too easy.
I have a.
Shall I distribute them? And you wanted to ask a question?
Yeah.
It can be said that the evidence for a photon as a single entity is a result of the way in which we measure electromagnetic radiation, namely with the photoelectric effect.
Yes.
That is, we do not see the photon, instead we see the electron that the photon excited,
Yes.
and then we infer
That there was something.
that there was something that, since the electron is quantized, they're numerable, 1, 2, 3, the photon, or whatever stimulated it to appear in the conduction band of the detector, must also have been quantized like the electron. But that's not necessarily true.
They are so small that it's extremely difficult to study. And we are happy to have some new experiments in the line.
Any further questions? Then let's you think.
I apologize for the beginning.
Well, I'm happy.